Hello and welcome back for some more reinforced concrete design. Now that we've covered all the theory pertaining to shear, let's solve an example. So before we begin the example, let's quickly go over the shear design procedure. So you might see here on this slide, the layout of the procedure is maybe slightly different from what you've encountered in other lectures or books. And I've just laid it out in a way that really makes some of the checks come first so that you can change the section if you need before moving further. So here we need to calculate the shear force in the section at a distance d, so that effective depth from the support. There then is a basic condition that we need to satisfy. And if we don't satisfy that condition, then we need to redesign or rethink our section. We also want to check that the concrete can resist the shear without crushing. Once we've done those two checks, we can find the shear resistance of the member without any reinforcement, VRDC. And once we've found that, we can look at the minimum shear links that are required. After looking at the minimum shear links, we can then design links at any other place that requires them and determine the extent of the minimum links. So that is basically the procedure we're going to follow. And this is the exercise that we're going to demonstrate the procedure on. We've got a 12-meter spanned, simply supported beam. There's a load of 45 kilonewton per meter on it, which includes self-weight. We can see here the cross-section of that beam breadth of 350 millimeters, an effective depth of 550, and we can see here that the reinforcement for bending has already been calculated with 4 bars of 32 in the tension zone and 2 bars of 20 in the compression zone. We're also given the strengths of concrete and steel, and we need to design the shear reinforcement. So, as always, we are using calculation sheets for this. In calculation sheets, we have the heading at the top, which will normally include the company, the project, the page number, who is the engineer designing, who is the engineer checking, and other information. There are 3 main columns. The first left column is the references. So where is this information from? For example, what equation in the code? In the middle, you do your calculations, and on the right-hand side, any output that we're taking forward. I've started by laying out what we know in the calculation sheet, so the input, so the span length of 12, the ultimate design UDL of 45 kilonewton per meter, the strengths of concrete and steel, and the drawing of the cross-section. The first thing we need to do is figure out what the design shear is. And for that, we start off by calculating the shear in the beam. Now, this is a simply supported beam with a span of 12 and a UDL of 45. So it's pretty easy to figure out the maximum shear, which will be at the supports. That'll be the reaction. So it'll be the whole load, so 45 times 12, divided by 2, half at each reaction. And we get a maximum shear of 270 kilonewtons. Now, according to the code, we can use the reduced design shear, which is at a distance d from the support. So if this is our shear diagram, we need to find VED, so the reduced design shear, at d from the support. Now, according to our sketch, we already know that the effective depth is 550 millimeters or 0.55 meters, and therefore VED is going to be the maximum shear and take away that part of the UDL that's already been covered. So 0.55, the distance, times 45, the UDL. And if we do that, we end up with a VED of 245.25 kilonewtons. Now, once we've done that, we always need to do this check before we continue. Shear force VED must always be smaller than 0.5 times BW times D times nu times FCD. So let's look at each one of these things. Nu is the strength reduction factor for concrete cracked in shear, and it is 0.6 times 1 minus FCK, the strength of concrete, divided by 250. The only variable we have to add in here is the strength of concrete at 30, and we get that nu, the strength reduction factor, is 0.528. And that means that we have everything to complete the equation. So VED, our 245.25, needs to be smaller or equal to 0.5 times BW, the breadth of the section, which is 350, times D, the effective depth of the section, which is 550, times nu, which we've just found at 0.528, and times FCD, which is the strength of concrete divided by the safety factor, which is 1.5 for concrete. And we times that by 10 to the minus 3, because FCD is in megapascals, and I want this to be represented in kilonewtons so that I can easily compare it to VED. And if we calculate that, we get an answer of 1016.4 kilonewtons, which is definitely bigger than the VED that I calculated. Moving on, I want to check what is the maximum resistance of the section without the concrete crushing. And to do that, I need to figure out what VRD max is. So in VRD max, I can see that there's alpha CW, BW, Z, nu, which I've just calculated, FCD, which I know, and cotan and tan theta. So I'm going to start off by finding theta. And it's this equation, which does look quite complicated, but actually we do know everything. So within the brackets, I've got 5.56 times VED, which we've calculated as 245.25. The 10 to the power 3 is to organize my units. And I can see here in the denominator, I have BW 350 times D 550, and then I have FCK, the strength of concrete, 30 twice. And if I calculate that, I find that theta is 7.78 degrees. Now, if you recall from the lectures and from the theory that we've discussed, the angle for this strut model, or this equivalent truss model, has to be between 22 and 45 degrees. Now, in this case, 7.78 is definitely under 22 degrees. And that means that I have to take the minimum allowed angle of 22 degrees, which means that cotan the angle is 2.5 and tan the angle is 0.4. Alpha CW is 1 if we assume that there's no axial load in the beam, and we've not been given any, so that is reasonable to assume. And now we can calculate VRD max. So VRD max is going to be alpha CW 1, the breadth of the section 350, times Z, the lever arm, which in shear is 0.9 times D, so in our case 0.9 times 550, times the strength reduction factor that we've just found of 0.528, and then times FCD, the strength of concrete divided by the safety factor for concrete, which is 1.5, and divided by cotan and tan, the angle. All that multiplied by 10 to the minus 3 in order to get kilonewtons, and I get that VRD max is 630.86 kilonewtons. And that means that I am not in danger of the concrete crushing because the maximum shear that I have is 245.25. At this stage, I want to find VRDC. VRDC is the design shear resistance of a member with no shear reinforcement. So what can the concrete resist in shear without me adding any reinforcement? And to figure out this equation, we do need to calculate a few things. The first thing is CRDC, which is derived from tests, and it is 0.18 divided by the safety factor for concrete, which is 1.5, so CRDC works out as 0.12. The size factor K, there are indeed a lot of Ks in reinforced concrete design, is 1 plus a square root of 200 over D. We know everything here, and that works out as 1.603. That has to be smaller or equal to 2, which in our case works out. We also need to calculate rho L, which is the reinforcement ratio for the longitudinal steel. Now, we need to calculate the area of that longitudinal steel. We have 4 bars of 32, so it is 4 times the area of 1 bar, and that works out as 3,217 millimeters square. And we need to divide that number by BW times D, 350 times 550, and that works out as 0.0167, and that number, rho L, needs to be smaller or equal to a ratio of 0.02, which it is. So just a reminder of what that equation looks like for VRDC, and we can add here K1, which is 0.15, and sigma Cp, which is 0 because we do not have any axial force in this example. And now we have all the variables and we can put them all in the equation to find out what VRDC is. So CRDC 0.12 times K 1.603 times 100 times the reinforcement ratio of 0.0167 times FCK, which is 30, all that to the power of a third, plus 0 because we already agreed there was no axial force, and all of that times BW 350 times D, the effective depth, 550, and once again 10 to the minus 3 to organize my units into kilonewtons. And I find that VRDC is 136.5 kilonewtons. Now, before I come to any conclusions, I need to do one more check on this. And that check is that VRDC is bigger or equal to nu min plus K1 sigma Cp times BWD. Nu min is 0.035 K to the power of 1.5 times the square root of FCK. We've already found K in the previous slide as 1.603, and we know what FCK is, so we can find out that nu min is 0.389. And if we add that to the fact that we know that sigma Cp is 0, we can find out that VRDC needs to be bigger than 0.389 times 350 times 550 times 10 to the minus 3 to organize my units, and that works out as 74.9 kilonewtons. And the VRDC that I calculated is indeed bigger than this. So now I can come to a conclusion. And that is that VRDC, so what the concrete can resist without any shear reinforcement, is less than the applied load VED. And that means that I do need to design shear reinforcement. I'll start out by calculating the minimum shear reinforcement that I need. And that is because sometimes the minimum shear is enough to carry over the whole section. But we'll see how far we can get. As you know, in the middle of the section, the shear is 0. And that's where the maximum bending is as well. But that means that the closer I get to that shear of 0, I really probably only need to put minimum shear reinforcement. Minimum shear reinforcement is calculated using the ratio of the area of the minimum reinforcement steel divided by the spacing between those shear links. And that equals 0.08 times the square root of FCK times BW, the breadth of the section, divided by the strength of the steel. So in our case, 0.08 times the square root of 30 times 350 divided by 500. And that ratio equals 0.306. Now, this is a ratio, and I have two unknowns here. What is the area of the minimum shear reinforcement, and what is the spacing? So I need to assume something before I can continue. Let's assume that the minimum shear links have a diameter of 8 millimeters. Now, if I assume that, I can isolate S min, so the spacing between those links, and write it as the area of the minimum links divided by that ratio that I just found. Now, note here that when I calculate the area, I need to take 2 bars of 8 millimeter diameter. And that is because the way that shear links are, as a rectangle around, means that there's resistance on the right hand and on the left hand, and that is the dimension of a bar because it goes in a loop. So essentially every loop gives me twice the area of resistance, one on each leg of the link. And therefore the area is 2 times pi times 8 squared over 4 divided by the ratio of 0.306. And that gives me a spacing of 328 millimeters. Now nobody is going on site to measure those 328 millimeters. We need to come to something a bit more pragmatic and obviously smaller than what is required, right? So we want to put more rather than less than what is required. So in this case, let's take a diameter of 8 every 300 millimeters. If we do that, we can also calculate what the shear resistance of those minimal links are. So VRD min, what we're providing as minimal shear links, is the area of those links divided by the spacing between them times FYWD, which is the strength divided by the safety factor, times D, the effective depth, times cotan, the angle, which we already discovered is 2.5. So here we have everything. I just need to multiply by 10 to the minus 3 to organize my units into kilonewtons, and I get that the minimum shear links already cover up to 200.33 kilonewtons. And that means that any place along the beam where the shear is less than 200.33, I only need to provide minimum shear links. But what about the places where it's over? Well, there I actually need to design the shear links, which is what we're doing now. So once again, I have a ratio, so the design shear links divided by the spacing between them needs to equal VED, and that is my design shear of 245.25, divided by Z, which we already said in shear, that's 0.9 times the effective depth, so 0.9 times 550, times FYWD, strength of steel divided by the safety factor for steel, 1.15, and times cotan the angle, 2.5. multiplying by 10 to the power of 3 to organize my units, because the strength of steel is in megapascals, which is newtons per millimeter square. The VED I've given in kilonewtons. Organizing that, I get a ratio of 0.455. Now, once again, here I need to design something. I need to either give the spacing or the area in order to figure out what those design shear links are. Let's continue to assume a diameter of 8 millimeters. And in this case, my spacing becomes the area of those shear links. So once again, 2 times the area of 1 bar divided by the ratio that we just found, which is 0.455. And in this case, the spacing works out as 220.9 millimeters. Now, you might say that it would be okay to take 220. I feel this is a little bit too close, and so I'm going to provide these design shear links at every 200 millimeter spacing. We also need to check the maximum spacing restriction. So the maximum spacing restriction has to be 0.75D and also smaller or equal to 600 millimeters. So in this case, we meet the maximum spacing restriction. And the very last thing I want to do is I want to think, where can I put my minimum shear links? Obviously, the closer I get to 0, they're definitely going to be there. And where do I need to provide the shear links to cover the 245.25 kilonewtons? So you can see here, I've drawn out the shear. At a distance of D from my maximum shear that I calculated in the beginning, I've got VED, 245.25. And between that 245.25 and the minimum shear link resistance of 200.33 kilonewtons, in that distance there, I'm going to provide a diameter of 8 every 200. But once I am under that 200.33, I can just provide my minimum shear links of a diameter of 8 every 300. I've drawn it out in this little sketch to kind of make it obvious what I need to calculate here. If I can figure that x, that distance between VED and Vmin, I can then know exactly where I put the design shear links and where I put the minimum shear links. And to do that, I can just use similar triangles, or you can use the UDL or any other method. So using similar triangles, I can find the extent of the design shear links, as we said, that x, and I can say that VED divided by 5.45, which is essentially the distance from VED to the middle, so 6 meters, take away 0.55, which was the D, has to equal, because it slopes at the same angle, the Vmin divided by the distance that's left to the middle, which is 5.45 take away x. Just introducing the numbers for VED and Vmin into here, and then isolating x, and I get that x equals 1 meter. So after I've passed D from the support, I go for 1 meter with a diameter of 8 every 200, and then until I get to the same distance from the other side of the support, I can just put my minimum shear links of a diameter of 8 every 300 millimeters. And that is the shear for this beam. I hope that was helpful, and I hope it helped bring some of the theory we discussed to life using an example. Join me when we solve some more examples and discuss some more reinforced concrete theory.